In this lesson, we shall focus on chemistry. Physical sciences, paper 2. Normally, when you actually writing the chemistry paper, it is very important that you start each question on a new page. Hydrogen gas is prepared by the reaction of methane and steam. This is a chemical equation. In this chemical equation, what are we preparing? We are preparing hydrogen gas. So now, to actually produce hydrogen gas, we conduct a chemical reaction of methane and steam, as shown in the following balanced chemical equation. We have a balanced chemical equation in which we are mixing two substances, namely methane with the chemical formula CH4 as a gas, and water as steam, water in gaseous state. And the reaction is in equilibrium because we can see it is proceeding in the forward but also in the reverse directions. The products are carbon monoxide gas and hydrogen gas. Methane CH4 and steam H2O are sealed in a 2 cubic decimeter container. We are mixing methane with steam, which is water in gaseous state. To react are allowed. In other words, we are mixing methane and steam, and these are sealed in a 2 cubic decimeter container to react, and they are allowed to reach equilibrium at temperature T. Now, the first question is, state Le Chatelier's principle for 2 marks. State Le Chatelier's principle for 2 marks. This is the principle for those who forget the principle. We state it as follows. When the equilibrium in a closed system is disturbed. The system will reinstate a new equilibrium. By favoring the reaction that will oppose the reaction that will oppose the disturbance. And this is worth 2 marks. We repeat the Le Chatelier's principle in words. When the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. Now, pay attention. We are starting and dealing with actual reactions in equilibrium. We are dealing with reactions in equilibrium. But we're then saying Le Chatelier's principle works if we disturb the equilibrium. So when the equilibrium in a closed system is disturbed, so you're disturbing the equilibrium in a closed system, the system will reinstate. So if you disturb the equilibrium, the system attempts to reinstate or to establish a new equilibrium by favoring the reaction that will oppose the disturbance. So what then happens is the system tends to reinstate. How does the system establish a new equilibrium? It reinstates a new equilibrium by favoring the reaction that will oppose the disturbance. And this, so now it tends to actually establish a new equilibrium by favoring. It favors the reaction that will oppose the disturbance. And this is called Le Chatelier's principle. 2 marks. 2 marks. Next question. Use the Chatelier's principle to explain how the following changes will affect the yield of hydrogen gas. Use the Chatelier's principle to explain. Use the Chatelier's principle to explain how the following changes will affect the yield of hydrogen gas. Adding more methane. If you look at this chemical equation, methane is a reactant. So if you add more methane, you increase the amount of methane in the reaction. How will this affect the yield? How will this affect hydrogen gas? And this is what we say. In other words, you put more of this reactant. Remember, we are mixing CH4 and water in a 2 cubic decimeter container, and when you mix them up in the container, you get the following products: carbon monoxide and hydrogen gas. If now you suddenly stuff up, you increase, you just put more CH4, more CH4, more CH4 gas, what then happens? This is actually exactly what happens. This is what we say. So we then saying adding more CH4 will increase the concentration of CH4. Okay, now what we notice, if you add more CH4, adding more CH4 will increase the concentration of CH4. Putting more CH4 means that you are, by so doing, increasing the concentration of CH4, because concentration is number of moles over volume. Concentration equals number of moles over volume. Concentration becomes number of moles over volume. Next, this means that the forward, if you put more CH4, it means the forward reaction is favored. The forward reaction is favored. It means the forward reaction is favored. You put more CH4, you are increasing the concentration of CH4. Therefore, it means putting more CH4 will increase the concentration of CH4. And by so doing, it means the forward reaction is favored. The yield. The yield of hydrogen gas will increase. It means that if you increase the concentration of CH4, the reactant, the yield of hydrogen gas will increase. So, in other words, the yield of the hydrogen gas will shoot up. It is expected, therefore, that we will have more hydrogen that is going to be formed in this chemical reaction. The delta H in grade 11, it is very clear that the heat of reaction ensures that as a grade 11 learner, you need to understand that this reaction here is endothermic, because the delta H is plus 206 kilojoules, and therefore it is endothermic. So we're dealing with an endothermic reaction at grade 11 level. Okay. Now, 3 marks. We've got the 3 marks. Because they're saying use the principle we stated, Le Chatelier's principle, to explain. So you must explain how the following changes will affect the yield of hydrogen. If you just are conducting a chemical reaction in which you're adding CH4 in water and H2O gas. So now you are mixing them up, these two gases of methane and water. Methane is CH4. You know that from grade 11. And water is H2O. But water is steam if it is a gas. Okay, we call that steam. Right, so in the end, you are mixing methane and water in a container whose volume is 2 cubic decimeters, and you mix them up. But when you're doing the mixing, what you're then having is there is a product, namely carbon monoxide and hydrogen gas. There are 2 products that form there. But now the question is, the examiner is saying you need to explain how the following changes will happen. If another student comes to you, you are busy in the lab there, you are busy in the science laboratory, and the student says they start adding more CH4 in the container. They start adding more CH4. You're like, stop. I've put enough CH4. I've put enough methane gas. And the student says, I'm putting more. If they put more without your permission, in the end, then what do you expect? Are you going to have more hydrogen or less? This is the explanation. Because the examiner is saying, tell us about the yield of hydrogen. Because somebody adds more of the CH4. Adding more CH4 will increase the concentration of CH4. Adding more CH4 gas will increase the concentration of CH4. This is the sentence. Adding more CH4 will increase the concentration of CH4. Now, we understand that. When we increase the concentration of CH4, it means the forward reaction is favored. The forward reaction is favored. If the forward reaction is favored, it means we have more products. More products. Okay. And therefore, the yield of hydrogen will increase. 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 And these are the 3 points. Next question. The examiner in 6.2.2 is saying a decrease in the volume of the container. This volume initially is 2 cubic decimeters. And the examiner says, okay, suddenly we make it smaller. Maybe we'll make it 1 cubic decimeter. We make it smaller. From the bigger container to a smaller container. Yeah? And then now the question is how it is going to affect the hydrogen. How is it going to affect the hydrogen gas? Okay, let us reason together in this case. So we reason in terms of grade 11. And the grade 11 curriculum is clear about the relationship between volume and pressure. So you know that pressure from grade 11 and volume are inversely proportional to each other. Because if you decrease the volume, then you increase the pressure. And therefore you increase the concentration. Okay. You need to explain how the following changes will affect the yield of hydrogen. So if you decrease in the volume of the container. So you make the container smaller. How will this affect the hydrogen? Let's analyze this together. So now we note that an increase in pressure, an increase in pressure favors the reaction. Favors the reaction that produces that produces the lower number of moles or number of molecules. Number of molecules. Pay attention. An increase in pressure favors an increase in pressure favors the reaction that produces a lower number of moles. So if you increase the pressure, what that does is it favors the reaction that produces a lower number of moles or number of molecules. You increase the pressure, the lower number of moles, you have 1 mole of methane CH4, 1 mole of water, gas, or 1 mole of water is steam, 1 mole of carbon monoxide, 3 moles of hydrogen. So if you increase in pressure favors the reaction that produces a lower number of moles. Lower number of moles means you are favoring the reverse reaction. Lower number of moles means you are favoring the reverse reaction. Lower number of moles, it means you are favoring the reverse reaction. An increase in pressure, if you increase the pressure, you need to look for the lower number of moles, 1, 1 versus 1, 3, and therefore 1, 1, it means that an increase in pressure favors the reaction that produces the lower number of moles or number of molecules. Next, because now the lower number of moles are in the reactants on the left of the chemical equation, it means the reverse reaction is favored. The reverse reaction is favored. The reverse reaction is favored. Third point, it means the yield. The yield of hydrogen decreases. 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 So an increase in pressure favors the reaction that produces the lower number of moles or number of molecules. And you can see the lower number of moles are actually on the left, and on the right you have 1 mole of carbon monoxide and 1 mole of hydrogen. And on the left you have 1 mole of methane gas, CH4, 1 mole of water, steam, H2O. So an increase in pressure favors the reaction that produces lower number of moles, and it means the reverse reaction is favored, yeah? Reverse reaction is favored. The yield of it, if the reverse is favored, it means that we are using up the products, we are using up hydrogen, we are using up carbon monoxide, and therefore it means that the yield of H2 gas decreases. Hydrogen gas decreases. And this is our observation. We move on to the next question. Okay, I wanted to also mention that at grade 11, we learn about these here. But at grade 11, we are taught about exothermic and endothermic reactions. But we are told that if the heat of reaction is positive, it means that the kind of reaction we're dealing with is endothermic. It means that we're dealing with an endothermic reaction. If the reaction is endothermic, it means that it's a reaction that requires heat to proceed. And now it means this particular reaction absorbs much heat. Okay, so this is what we are able to observe there from grade 11. But also we have noted the relationship that is come and has been mentioned here, the relationship between pressure and volume. That if you decrease the volume, like for example, you decrease it from 2 cubic decimeters to 1 cubic decimeter. You make the volume smaller. It means that you are increasing the pressure. The pressure becomes so big. When the pressure becomes so big, because of the inverse relation between pressure and volume, and this is Ohm's law. This is Boyle's law. This is Boyle's law. The inverse relation between pressure and volume. Pay attention. Now we are looking at the graphs. There's some graphs in chemistry that you need to understand, because when you're doing the exothermic and endothermic chemical reactions, you need to understand graphs. You need to understand graphs. There are specific graphs we're going to do in detail for both grade 11 and grade 12. Okay, but I know very well that the guys who are writing tomorrow, they're writing their chemistry paper. It is the grade 12s. The grade 12s are writing their chemistry paper tomorrow. So it's very important that we actually make sure that the grade 12s understand their chemistry, because they have their chemistry provincial paper, the trial paper written in September. It's coming tomorrow for the grade 12s. And we need to make sure that when they sit for the trial paper tomorrow, the grade 12s, they know their chemistry very, very well. And that enhances the reason why I'm doing this chemistry and I'm doing this paper. This paper I'm doing was written last year, September, by the matrics, who wrote the trial metric paper in the Gauteng province last year. Right. Hydrogen gas is prepared by the reaction of methane and steam, as shown in the following balanced chemical equation. CH4 gas reacts with steam H2O, which is water in gaseous state, to produce carbon monoxide, CO gas, and hydrogen gas. And this here is an endothermic chemical reaction. Please take note of that, grade 11 children. Now, the methane gas CH4 and steam H2O are sealed in a 2 cubic decimeter container to react and are allowed to reach equilibrium at temperature T. So they reach equilibrium at temperature T. Okay, there's some temperature at which these particular reactants reach equilibrium. Because what is happening here? We take these here and we put them in a container. So in this container, we put the following, yeah? We put CH4. And also we put CH4 gas, but we also put H2O gas. We put them together. We put them together. When we mix them together, we mix them together in the container. Okay? Write down a reason. And what are we able to see here? You can see there is H2, hydrogen. The hydrogen graph begins from the origin and begins rising up. And then it begins to level up from time 1 to time 2. And that is what we're able to see with H2 graph. The CH4 graph, which is the methane graph, begins from the number of moles on the vertical axis, a number of moles of 1.4, and we're able to see a decrease in the CH4. So in other words, the number of moles of methane gas, actually this number of moles decreases. Similarly, we are able to see a graph that is decreasing, and it's labeled the water graph, the steam graph, H2O. It begins from 1.2 number of moles and it begins decreasing. It begins leveling off from time 1 to time 2. Now, carbon monoxide, CO. We can see it is an increasing graph from the origin, rises up, begins leveling up from time 1 to time 2. Okay, let's answer the questions that the examiner is asking us. Write down a reason why there is no change in the number of moles of each of the gases between times T1 and T2. Times T1 and T2, all the graphs are level. There's no rise, there's no decrease, but level. Give a reason why there's no change in the number of moles. The vertical axis shows the number of moles, and you can see the number of moles is level. Why is this the case? Why is this the case? Okay, let's answer that question to explain why the graph is level. Why is the graph level? From time 1 to time 2, all the graphs, CO is level. The H2O graph is level. The CH4 graph is level. The hydrogen graph is level. They're all level. They're not either increasing or decreasing. Why are they level, these graphs? Why? Because we are starting a reaction that is in equilibrium. How do we see that this reaction is in equilibrium? It proceeds in both forward and reverse directions. Both forward and reverse directions, and we're looking at reactions in equilibrium. And this reaction is allowed to reach equilibrium at a temperature T. We know that when we study reactions in equilibrium, something is very important. Either most of these are endothermic or exothermic reactions. If they're exothermic reactions, it means, therefore, the heat of reaction is negative. If the heat of reaction is positive, it means we are starting endothermic chemical reactions. We proceed as follows. 6.3. Why are the graphs level? Why are they level? Why are they not increasing from time 1 to time 2? Why? This is the reason. The reason for the level graphs when you're studying reactions in equilibrium is because the reaction is in dynamic. Dynamic or chemical. Chemical equilibrium. The reason why these graphs are level, it's simply because the reaction is in dynamic. We say it is in dynamic. Dynamic equilibrium means it proceeds both in the forward direction and also in the reverse direction. Another learner is going to come and say, I don't like saying they're in equilibrium. I don't like you saying the reaction is in equilibrium. I don't like that. I don't like saying the reaction is in dynamic equilibrium. I don't like saying the reaction is in chemical equilibrium. I don't like using these words, but the learner can come and say, I'm a learner who likes saying the rates. The rates. The rates of the forward. The rates of the forward and reverse. The rates of the forward and reverse reactions. The rates of the forward and reverse reactions are equal. The rates of the forward. So now, the fact that these graphs are level, it means that the rates of the forward and reverse reactions are what? Are equal. The rates of the forward and reverse reactions are equal. That is why this happens when the graphs are level. When the number of moles of the graph does not change. It doesn't matter what it is here, but it does not change. It doesn't matter what it is here, but it does not change. It doesn't matter what it is here, but it does not change. It doesn't matter what it is, the number of moles doesn't change. It doesn't change. It doesn't change. The number of moles does not change. So this means the rates of the forward and reverse reactions are equal. So this is true for reactions in equilibrium. So when a reaction is in equilibrium, it means the rates of the forward and reverse reactions are equal to each other. If you don't want to use rates, you can say, hang on, if the reaction is in equilibrium and the graphs are level like this, it means the reaction is in dynamic or chemical equilibrium. Dynamic or chemical equilibrium. We move forward to the next question. We move forward to the next question. In our chemistry paper, it is very important that we're able to read graphs very carefully, but also that we're able to perform chemical calculations. We must be able to calculate the number of moles. We must be able to find volume. We must be able to understand the STP conditions, standard temperature and pressure conditions. 6.4 is here. Use the information on the graph and calculate the equilibrium constant for this reaction at temperature T. Use the information on the graph and calculate the equilibrium constant, Kc, for this reaction at temperature T. Let us calculate this one. We need to calculate the Kc. How do we calculate Kc? We need to first draw a table. And now to draw the table, we need to use the rise technique. We need to use the rise technique. The rise technique says you must first look at the reaction. The reaction means you have CH4, H2O, carbon monoxide, and hydrogen. And then you'll quickly have what we call the initial amount. Initial amount in moles. The initial amount in moles. Change in amount. Change in amount. Change in amount in moles. Equilibrium amount. Equilibrium amount. So we need to learn how to draw this table, grade 11 and matrix. Please. You need to learn how to draw this table. Here we're looking at the equilibrium. Equilibrium amount in moles. Concentration. Concentration at equilibrium. Concentration at equilibrium. Let's deal with CH4, steam, carbon monoxide, and hydrogen gas. Now, we look at this carefully. We start with CH4, water. If you look at this graph very carefully, initially CH4 is 1.4 moles. CH4 is initially 1.4 moles. 1.4 moles. Meaning this is the initial number of moles of methane gas. 1.4. And then here you have water. Water. And we have water whose initial number of moles in the beginning here at time T0 is 1.2. Water begins at number of moles of 1.2 and number of moles decrease. 1.2. Then you have that in the beginning of this chemical equation, you had no products at all. You only had the reactants. You only had in the 2 cubic decimeter container, you only had methane and steam, and these were mixed together. Okay, we proceed. At equilibrium, we can see that in this part of the graph, we have what we call equilibrium. Okay, if you have equilibrium in this part of the graph, what then do we have here? Equilibrium means, therefore, the number of moles doesn't change. And it is what we're seeing here. The number of moles doesn't change. All these graphs are level. All these graphs are what? Are level. Okay, so this hydrogen graph is level, methane graph is level, CH4, water, steam, H2O graph is level, also carbon monoxide graph is level. Now, pay particular attention. If these graphs are level, something must be given at equilibrium here. And now, here we have equilibrium. Equilibrium. Right, we have equilibrium here, but we can see that the number of moles is actually 0.6. So we have 0.6 moles. 0.6 moles of CO, 0.6 moles of carbon monoxide at equilibrium. At equilibrium, therefore, you have 0.6 moles. 0.6 moles of carbon monoxide at equilibrium. Put it in the right block, 0.6 moles at equilibrium. Next. Then you need to come and then say, you actually have changes here. So you must complete the changes row in the table, and you must learn how to do this because you expect to learn this as a chemistry student. Now, to do the changes, there's some things you need to know. You need to look at the number of moles. 1. So here you have, for every 1 mole of CH4, there's 1 mole of that, there's 1 mole of steam, 1 mole of carbon monoxide, 3 moles of hydrogen gas. So now, it means that you added to 0. There was 0 in the beginning. It means that you added 0.6 to 0. If you add 0.6, you get 0.6. You did not have any product before. But if you add 0.6 to 0, you get 0.6. Hydrogen gas. You will come to hydrogen. But the hydrogen is very interesting because with carbon monoxide, they're not in a 1-to-1 ratio, but in a 1:3 ratio. And you're going to use our calculator because for every 1 mole of carbon monoxide, you have 3 moles of hydrogen gas. So now you take 0.6 by 3, which is 1.8 moles. 1.8 moles. So now you have exactly 0.6 times 3, which is 1.8 moles. Meaning here, you're going to have change in the amount, which should be 1.8 moles plus 1.8 moles. Okay, because 1:3 is the mole ratio for the number of moles of carbon monoxide to the number of moles of hydrogen gas. Okay, these are the changes. But now these changes which are 1, 1, 1, it means therefore you're going to just do, it's for every 1 mole of carbon monoxide, you have 1 mole of methane gas. And therefore, if the change is 0.6, it's going to also be 0.6 here. Okay. And also here, if the change is 0.6 for every 1 mole of CO, carbon monoxide, it's also going to be 0.6 there for the steam. Okay. Now, these changes here, we regard them as negative changes. So because the reaction proceeds in both the forward and the reverse, but looking at the forward direction, you're going to actually consider these as negative. Meaning you're going to say 1.4 minus 0.6. 1.4 minus 0.6. 1.4 minus 0.6. So that's what we're going to do. 1.4 minus 0.6, which is 0.8. 0.8. So here we're going to have exactly 0.8. 0.8. And then you're going to have, you're going to have, you're going to have here 1.2 minus 0.6. 1.2 minus 0.6, which is 0.6. 0.6. And then here you add 0 plus 1.8, you get 1.8. And this would be the equilibrium number of moles. And now you must also be in a position to read chemistry graphs as both grade 11 and grade 12 learners. Now, but we know that concentration is what? Concentration is number of moles over volume, right? The volume is 2 cubic decimeters. So you're going to take 0.8 number of moles divided by the volume, number of moles over volume. And when you divide here, you get 0.4. You take 0.6, which is the number of moles at equilibrium. You divide by the volume of 2 cubic decimeters, and you get exactly 0.3. You take the 0.6, you divide by 2, you get a 0.3. 1.8, you divide by 2. If you divide 1.8 by 2, you get actually exactly a 0.9. I know you can be able to quickly guess that one. So you actually be able to see that it is 1.8, you divide by 2, which is 0.9. 0.9. 0.9. Pay attention. We have actually completed this table. This table has been filled up. And therefore, in 6.4, you need to be in a position to explain exactly what to do here. So we want to calculate the equilibrium constant Kc. The grade 11 and grade 12 learners need to be aware of this, so that in the end, we look at this particular chemical equation and we take the concentrations of the products. Concentration of carbon monoxide gas, concentration of hydrogen gas, you cube it. You divide by the concentration of methane gas multiplied by the concentration of water. Sim. Go back to the table. Read off the values. What is the equilibrium concentration of CO? Right, the equilibrium concentration of carbon monoxide, you'll be able to see that is 0.3. 0.3, 0.3. So you're going to put 0.3 here. Hydrogen, 0.9. CH4, 0.4, 0.4. H2O, 0.3. So that in the end, so 0.3, 0.3 times 0.9, you cube it. 0.4 times 0.3. And therefore, we're getting 1.8225. 1.8225. 1.8225. So you're getting 1.8225. Right, and therefore these you can round off to 1.82. But Kc is dimensionless. Kc is dimensionless. It means what? It means that it has no dimensions. It has no units. Kc has no units. Grade 11, grade 12 learners, pay particular attention to this and make sure you understand this as we proceed to the next question. But note that when you're doing this, because I know there's some students who have never seen this here, but I'm just discussing this because there's some students who are writing this chemistry paper tomorrow. So what is very important is that when doing Kc, you must take the concentrations of the products and divide by the concentrations of the reactants. These square brackets like these, they mean concentration. So if we write like this, we mean concentration. So it's not, these are not just fancy brackets. They mean concentration, this. So we mean concentration of carbon monoxide here, concentration of hydrogen gas, but you take the number of moles here, you put on top here as a power. This is how we do the Kc. But obviously the CH4 is concentration, so we don't put round brackets here. We put square brackets because that is what we do in chemistry. We move on to the next question. Now, there is a change here, and the examiner is saying the temperature T is decreased. The temperature T is decreased. So now the temperature, there's an equilibrium temperature that we recorded. But now the examiner is saying the temperature is made smaller. Somebody decreases the temperature. They make the system colder than before. How will this change affect the Kc value for the above reaction? Let's reason these together. We're dealing with a situation where the temperature of the equilibrium system is now decreased. Obviously, how will this change affect the Kc value? Now, the examiner wants to know how the Kc value is going to be affected. We need to write the words increase, decrease, or remain the same. Kc. CO. Hydrogen. CH4. H2O. Water. So we've taken the concentrations of the products and we divided by the concentrations of the reactants, and this is the Kc value. But the temperature is decreased. So if the temperature is decreased, what happens? Remember that this reaction, grade 11 kids, you need to know this. If the heat of reaction is positive, it means that this is an endothermic chemical reaction. Endothermic reaction. Right, so if it is endothermic, what does it mean? What is an endothermic chemical reaction? What is endothermic? How does endothermic differ from exothermic? How? How does an endothermic reaction differ from an exothermic chemical reaction? How? How do these differ? You need to explain. You need to explain. You need to explain. And the difference is in the fact that endothermic requires heat to go on. Right. So in other words, this one, endothermic absorbs heat, but exothermic releases heat to the surroundings. So now this one requires heat, and therefore, because its heat of reaction is delta H is plus 206, which is positive. Which is positive. So now what then do we have here? What then do we have here? It means, therefore, if the temperature is decreased, it means that because the forward reaction is going to be favored by an increase in temperature. So if the forward reaction is endothermic, then the reverse reaction is going to be exothermic. Learn this, grade 11 learners and grade 12s. So if the forward reaction is endothermic, the reverse reaction is exothermic. And now at this point, if you decrease the temperature, the exothermic reaction is what? The endothermic reaction is not going to be favored, so it's going to favor the reverse reaction. If it favors the reverse reaction, it means, therefore, what you're going to have? You're going to have that these concentrations of the CH4 and water will therefore increase. And when the concentrations of these here increase, that means that the Kc value will therefore decrease. And therefore, the Kc value simultaneously decreases. So obviously, is it decrease, remain the same, or increase? It is therefore a decrease. It is therefore a decrease. It is therefore a decrease. It is most certainly a decrease here. We move on to the next question. We move on to the next question. We move on to the next question. Okay. I want us to discuss electrochemical cells. I want us to discuss electrochemistry for the grade 11s and the grade 12s. Because you need to understand what you call the reducing agents and the standard reduction potentials, because the grade 11s and the grade 12s, they do STPs, standard temperature and pressure conditions. But I want us to look at what we call a galvanic cell. A galvanic cell. A galvanic cell is set up using manganese, using a manganese rod, Mn, and an unknown metal X. A galvanic cell is set up using a manganese rod and an unknown metal X. The initial EMF, which is the electromotive force measured under standard conditions, grade 11s and matrix, please take note of the standard conditions. But when we measure the EMF under standard conditions, we are told, therefore, the EMF is 1.05 volts. The electrons fall from manganese. So there's a flow of electrons, but the electrons flow from manganese to metal X in the external circuit. Right, in the external circuit. So now if you have a cell, this is the setup. This is the setup. The kind of cell we're speaking about here is an electrochemical cell. You put a beaker like this, you put a beaker like this. And then, let me put larger beakers. I want us to see very well. Larger beaker like this, larger beaker like this. Salt bridge. And then we put here, we put manganese rod. Mn rod. And then this one is going to lean on the side of the beaker. And then we're also going to put an unknown metal X. Here we put an unknown metal whose name is X. The initial EMF, so obviously what we then do, we are able to determine the EMF here. So we can measure, you can put a voltmeter here. Put a voltmeter, then we're able to measure the EMF, the electromotive force. electromotive force, and we measure it here as determined by connecting the voltmeter to the two rods. And it is 1,05 volts. The electrons flow from manganese. So if this is manganese, the electrons begin flowing from manganese to metal X. They flow in that direction to the metal X. This is the metal X. In the external circuit, this is happening in the wire, is the reaction that occurs in this cell spontaneous? Write down only yes or no. Give a reason for your answer. They're asking you the question, is this reaction spontaneous or not? Because you're just connecting the manganese rod with a metal X, and then suddenly you put a voltmeter here, boom, you're able to see that there's potential difference, and the electromotive force is 1,05 volts. The question we're asking is one, is this reaction exothermic? Is this reaction rather spontaneous or not? Is this reaction that occurs in this cell spontaneous? Grade 11s, you learn spontaneous reactions. Is it spontaneous or not? Grade 11s and matrix. We need to answer that question in question 8. Clearly, the answer to 8.1 is that yes, Mr. Examiner. Yes, it is spontaneous. Right. But obviously, give a reason for your answer for the 2 marks there. 1 mark for the yes, 1 mark for the reason. The reason is that the EMF, what we call the electromotive force, is greater. Is greater than 0. Is greater than 0. The electromotive force is greater than 0, or you can say that the EMF is positive. The EMF is what? Is positive. The EMF is positive. Because the EMF is positive, it is exactly positive 1,05, then we are able to see that this is a spontaneous chemical reaction. The reaction is spontaneous because the EMF we can see is positive 1,05 volts. Right. So that is what you're able to observe. Or another student can come and say, I don't like saying it is spontaneous because the EMF is positive. Because if the EMF is positive, because it is positive, then it means it is spontaneous. Learn it grade 11s and grade 12s. But we will come to this point and say, you can say also the reducing. Reducing and oxidizing. Oxidizing agents are used. Reducing and oxidizing agents are used. Reducing and oxidizing agents are used. Okay, because the reducing and oxidizing agents are used, and therefore at this point it is a spontaneous chemical reaction. Spontaneous chemical reaction, and we're able to see a positive EMF, and therefore it is spontaneous. It is spontaneous chemical reaction. We move on, and as we start what we call galvanic cells, and this one is a manganese rod and also an unknown metal X. An unknown metal X. Pay attention to the electrochemical cells in chemistry. Next question. Which electrode, manganese or X, is the anode? You took the beaker like this, and then you put the manganese here. You put the manganese rod, and then you put another thing like this, another metal. Bloom, you connect your voltmeter here. You're in the science lab and do this. To complete the circuit, you put your thing, your salt bridge, and then you put your cotton wool here. You put the tube. You put a tube, and this tube here, you put a solution. inside the tube called the salt bridge. Called the salt bridge. And then now you put a solution, a chemical solution. But this tube now, because this solution is going to run out, you take some cotton wool, you put the cotton wool here. You put the cotton wool at the end of the tube so that the salt you have put in there, it does not run out. This is a salt bridge, so you put salt in there. Okay, right. And this, so you continue. Okay, so you put the salt here, and then now you complete this, and then suddenly, bloom, you see a reading 1.05 volts, and that is the voltmeter reading, meaning there's power that is flowing there. So we do the following. Yeah, so let us analyze this question together. Let us analyze this question together. Let us analyze this question together. Which electrode, because now we're told one thing, the electrons flow from manganese to the metal X. The electrons flow from manganese to the metal X. So they flow from manganese to X. This is the direction of the flow of electrons. So the electrons are flowing this way. They're flowing from manganese to the metal X. Flow of electrons. Flow of electrons from manganese to the metal X. Here are the electrons and they're flowing like this. From manganese to the metal X. Which electrode? Here's the question for 1 mark. Which electrode? The mark is only 1. Which electrode, X or Mn, X or manganese, is the anode? Which one is the anode? So let us answer this question, because you just need to look at the flow of the electrons and then be able to answer that question. And because the electrons here, what you are told is that the electrons flow from manganese, and therefore it means that manganese is the anode. Manganese is the anode. Manganese is the anode. Manganese, it's the anode. That is the answer. How do you know that manganese is the anode? Because the electrons flow from manganese to the metal X, and therefore it means that the electrode manganese is the anode. And then now we get our 1 mark, and then we proceed to the next question, obviously with so much ease, but the allocated 1 mark, you can see the 1 mark there. You can see the 1 mark there. You just have to say manganese because the flow of the electrons flow from manganese to metal X, and therefore means that manganese is what? Is the anode. Manganese is the anode. Manganese is the anode. Now we go to 8.3. We go to 8.3. Use calculations to identify metal X. The question is, what is this metal X? Because you take a beaker like this, you take another beaker like this in the chemistry lab, and you put your manganese rod here, and then you put your X here, metal X, and then you put your voltmeter like this. Okay, you put them like that. Okay, do this. And then you put your cotton wool here, and this is your salt bridge. The salt bridge, you sort of complete the circuit. You complete the circuit. You complete the circuit. Use calculations to identify metal X. Use calculations to identify metal X. Let us use the calculations to identify metal X, because the question is, if we're able to see, and then this one is 1.05 volts. That is the EMF. If the EMF is 1.05 volts, the question is, what is this X? Because we know that we're dealing with manganese, but what about the X? We don't know the X, and then we must solve for X, okay? So to solve for X now, we proceed as follows in the chemistry laboratory. We use the formula E naught. Under standard conditions, this E naught has to do with standard conditions. So this is EMF is measured under standard conditions of temperature and pressure. So E naught cell is E naught cathode. E naught cathode minus E naught anode. E naught anode. So we then say E naught cathode is E naught cell is E naught cathode minus E naught anode. What is the EMF of the cell? We're told that it is 1,05 volts. It is equal to the cathode is the X. The anode must be exactly what here? It is manganese. Manganese is the anode. So if manganese is the anode, we go to the table of reduction potentials and we check what the manganese is going to be. Let us check this manganese over here. We check the manganese over there. If you check this here very carefully, let us see now table 4A. We're using table 4A, please, grade 11s and grade 12s. But now if you look at the table 4A, you can see the increasing oxidizing ability is upwards. Increasing oxidizing ability is upward. You can see the arrow is from the table. I've made it to lie down like this, but this is the top of the table. So the increasing oxidizing ability is at the top of the table, but the increasing reducing ability is at the bottom of the table. So now there's certain things that remain very important in our analysis of the chemistry. Where is manganese here? You need to look for Mn manganese. Look for manganese Mn in this table and identify it very, very well. Here is manganese. Here is manganese. So you can see the manganese here, and you can see that the manganese has its E theta value. Its E theta value. And so the E naught or E theta value is minus 1,18. Minus 1,18 for manganese. So we're going to come here and write it down. Minus 1,18 for manganese Mn. Now we can see that manganese 2 plus 2 electrons gives us manganese in its stable state according to the oxidation numbers, grade 11s. You need to recall oxidation numbers. Now let us move to this one here. So we said manganese is the anode, and we read from the table it is the reduction potentials is minus 1,18. Let us solve for X. 1,05, which is X plus 1,18. And we need to solve for X because they said identify the metal X, and therefore you have 1,05 minus 1,18. This paper was written last year in the chemistry by the chemistry learners. Please make sure you are able to follow these, both of you guys, because it is very, very important. So now you take the 1.05 and you minus 1.18. And therefore, what is the answer? The answer is actually minus 0.13 volts. Minus 0.13 volts. The question we are asking, if it is minus 0.13 volts, what kind of a metal is X? We check. What kind of a metal is X? So if we then say, look, remember this number here, because if we then say it's minus 0.13, minus 0.13, you need to look for minus 0.13 in the table. Where do we have minus 0.13 here? minus. So now these are positive, positive, positive. So you don't check at the top here because it's positive, positive, positive. And then now you have the middle of the table, which is the hydrogen, 0 volts, minus 0.13. There it is. There it is. It is lead. PB. PB. It's lead. PB. Minus 0.13 is lead. PB. So minus 0.13 is lead, which is PB. So which means that X is lead. PB. X is what? X is lead, which is PB. We have seen in the table. Identify the metal X. What kind of a metal is it? It is PB, and PB is lead. Okay. So we saw X is minus 0.13, X is minus 0.13. Look at the table of standard reduction potentials and look for minus 0.13. Minus 0.13, it's PB. But PB plus 2 electrons, which is lead 2 plus 2 electrons, gives us lead. Okay, and therefore we have the minus 0.13 and there's no other minus 0.13 there. And therefore it is lead that we're dealing with. X is equal to PB. So now what is the metal X? We're going to say that, Mr. Examiner, X equals PB. That is the answer. We look at the next question. For this cell, write down the two standard conditions, grade 11 and the matrix. You need to remember your standard conditions very well. Right. What are the two standard conditions? Grade 11s and the matrix. The standard conditions are done at both grades, and I emphasize at both grades 11 and 12. Now, the standard conditions are concentration. Their concentration, right? So the concentration is 1 mole per cubic decimeter. Concentration is 1 mole per cubic decimeter. Temperature. Temperature is 298 Kelvin temperature or 25 degrees Celsius. These are the standard conditions, but they want two of the standard conditions. Please, students, make sure you remember your standard conditions. The concentration is 1 mole per cubic decimeter. The temperature is 298 Kelvin, and it is, or you can say 25 degrees Celsius as well. These are the standard conditions when we're doing galvanic cells. Pay particular attention to these grade 11s and the matrix. Okay. Now, something that is very important is the cell notation that you need to learn. The cell notation. So to write the cell notation, we deal with the anode. And then what we do, we put the salt bridge like this, and then we put the cathode. What is the anode? Right. What is the anode? What is the anode? What then is the anode? What is the anode? We said the anode is manganese. And then we then said that the cathode it's going to be PB, lead. PB, which is lead. So now we have the following. Right, so we continue. Right, we continue. Okay. Right, so now we're going to say manganese is a solid because it's a rod. And then you have the manganese 2 plus according to the table of standard reduction potentials. And then you put the salt bridge because this is what you have like this. Ordinarily, you put the manganese here and then you put the metal X here. And then you put your salt bridge overhead. Salt bridge overhead like this. And then you put your salt bridge. And then you can put your salt there. But now you have your manganese there and the metal X. So you put the manganese like this. Then, but you start reading this, you have the manganese electrode. And then when you have the manganese electrode, this is the manganese electrode. Manganese rod. And then you have the solution, which is the manganate ion. So you have the manganate ion. You have your salt bridge. We put the 2 lines here. And then you come to the solution, lead 2 plus, and then lead. Right, and when you write like this, but now you can write more. I want you to learn how to write like this. There are more details I want you to include. So you can put the manganese in aqueous, then put 1 mole per cubic decimeter. And then you put lead 2 plus aqueous. And then this lead is standard conditions, 1 mole per cubic decimeter. And then you have the lead solid. Lead solid. So you can write like this in a bit in some more detail. So when you write these particular solutions, you put the concentration, which is the standard concentration, 1 mole per cubic decimeter, 1 mole per cubic decimeter. But now you put the manganese as a solid, you also put the lead as a solid. Your anode is put on the left and your cathode is put on the right. So these are the kinds of things you need to take note of. And then in the next question, 8.4.3, you need to write the reduction half reaction. What is the reduction half reaction? So because this one is the anode, and therefore the cathode is associated with what? With reduction. So in the cathode, then reduction takes place. And then in the anode, we say oxidation takes place. So now in 8.4.3, if reduction takes place, you need to write the reduction half reaction. Reduction is what? The gain of electrons is reduction. The loss of electrons is oxidation. So there's LEO, which stands for the loss of electrons is what? It's oxidation, and the gain of electrons is reduction, which means you have the lead 2 plus. Right, lead 2 plus 2 electrons would actually give us what? Would give us lead. Would give us lead Pb. And this here is reduction, the gain of electrons. Check this table of standard reduction potentials. Check the table of standard reduction potentials. Let us check lead here. Right, we saw lead, which is Pb, but now reduction is what? Reduction is the gain of electrons. And the loss of electrons is called what? The loss of electrons is called oxidation. Right, so obviously if you look at these 2 arrows, the downward arrow, because this is the top of the table, we're using table 4A. In the exam, matrix and grade 11s, you are given 2 tables, table 4A and 4B. If you go and look at the arrow that goes down, it shows the increasing, reducing ability. So if you go down, you actually are experiencing increasing, reducing ability. But if you look at the table 4A and you go up, increasing, oxidizing ability. Right. So that obviously as you go to the top, what you're able to find, for example, here is that you have lead. And lead itself is actually experiencing what you call the increasing oxidizing ability. And because of this, we therefore then say that lead itself is actually being reduced. Right. If lead itself being reduced, so reduction is the gain of electrons. So the gain of electrons means that we have lead 2 plus 2 electrons will give you lead. But you write one arrow because these are two arrows. So you write lead 2 plus Pp 2 plus 2 electrons gives you lead. And then you'll come here and then say that Pp 2 plus 2 electrons will give you what? Will give you lead. And this is the reduction half reaction. Reduction half reaction. This blue one is called the reduction half reaction. Reduction half reaction. We look at the next question. We look at the next question. The next question is about copper, pure copper and the purification. So you must know how to take pure copper and purify it. Okay, or even copper and purify it. Purification of copper ore to pure copper. When you take copper ore, that is a form of copper that is raw, that is not purified, but you want to make it clean, you want to purify it. Okay, so now you use chemistry to purify it so that the copper can be good and can be used in the transportation of electricity, in the copper cables, and many other electronic devices, okay, as conductors. Now we're then taking question 9. You need to start this question on a new page. The diagram below represents the purification of copper ore. In this diagram, this diagram represents the purification of copper ore to pure copper. We want to have pure copper in the end. The cell also contains zinc, silver, and platinum impurities. So this cell also contains zinc, silver, and platinum impurities. Right. So this cell here, you're able to see there's some impurities here. There's some dirty stuff that they've put here. These things they've put here are impure. These are dirty. They are full of dust. They are full of grime. They are full of soil from underground because this copper is extracted from underground and you are putting everything now inside this particular container. Now, the cell also contains zinc. It contains silver and platinum impurities. So it has zinc, Zn. So Zn is zinc, but it also has silver, Ag, but it also has platinum, Pt. It also has platinum, Pt, like so. And the cell also contains these things, 3 things: zinc, silver, and platinum impurities. The graph below, or the graph, shows the initial relationship between the mass of copper deposited versus time. What is the mass of copper deposited versus time? The time increases. The time increases. When the time increases, the mass also increases. Right, we can see that the graph is a direct proportionality graph there. It's a direct proportionality graph there. And I will need your maximum participation here, and I will ask some questions to make sure that everything is okay. So I will check and see what is happening here. I will check and see what is happening here. Write down the energy conversion that takes place in this cell. Write down the energy conversion that takes place in this cell. So we continue. We continue. Right. We continue. So now I'll need your maximum participation. So what I'm going to do, I'm going to ask you guys to participate a little bit. We are left with 27 minutes. Write down the energy conversion that takes place in this cell. In this cell, we've put a cell here. We've put a cell or a battery, and then we connect to the electrodes like this, and we have the solution here. So now I'm going to ask a question because I know that Nombuso has been sleeping. Nombuso has been sleeping. Nombuso, write down the energy conversion that takes place in this cell. If you put a cell here and then you connect to the rods and there's a solution, what um write down the energy conversion that takes place in this cell for 1 mark. Nombuso, what is the answer?
Sam,
Yes.
its electrical energy is converted to chemical energy.
Well done. It is electrical to chemical. Electrical to chemical energy. Correct. Well done there, Nombuso. So we are noting that we are actually converting electrical energy to chemical energy because we are connecting this particular cell here. It has electrical energy, and then we are converting it to what? To chemical energy. And we're moving forward to the next question. Right, at which electrode A or B would pure copper be deposited? At which electrode A or B, we need to choose A or B would pure copper be deposited. Remember, the solution here is copper sulfate, and then we have the impurities. These impurities have in them silver, they've in them zinc, they've in them platinum PT. Now, at which electrode would pure copper be deposited? A or B? Provide a reason for your answer. We're going to look at the reason, obviously, for that one. We can look at the reason for that one. But first, answer this question here. At which electrode, A or B, would pure copper be deposited? At which electrode, A or B, would pure copper be deposited? Right. At which electrode, A or B, would the pure copper be deposited? So obviously, I'm going to help you with this one. At this point, it's going to be electrode B that is pure copper be deposited. It is on this electrode that you're going to have pure copper being deposited. So when this reaction takes place, then you actually be in a position to see that there's going to be a buildup of copper that is going to be attached to this particular electrode, and it's going to be deposited to the electrode. We call these electrodes. It's going to be attracted to the electrode B. And obviously, because electrode B is associated with negative, and because the electric current will flow like this, right? And as a consequence, it will flow towards the electric current is going to flow towards electrode A, and the copper is going to be deposited to electrode B, and you're going to be seeing the reasons why the pure copper, because this is copper sulfate that is there, and the pure copper is going to be so we have pure copper that is going to be attracted towards the negative terminal or the electrode associated with the negative terminal of the battery. Okay, right, or negative terminal of the cell. So the pure copper is going to be actually deposited to electrode B there. Okay, we move on to the next question. And the reasons are going to be clear very shortly. Write down the half reaction that takes place at the anode. Write down the half reaction that takes place at the anode. Right. So now there's something that you need to realize here at this point, that the half reaction that takes place at the anode. We've already seen that what you're going to have here, you're going to have a lot of the buildup. The question, therefore, is that what cell half reaction takes place at the anode. So you need to refer to these here. You need to refer to the half reactions potential. Refer to the half reactions potential and look for copper. Look for copper. Copper is Cu. Right, and then you look for this copper, this one. This copper, this one, is sitting there, and you have copper 2 plus 2 electrons gives you copper. Right, so you have copper 2 plus 2 electrons gives you what? Gives you copper. And therefore, at this point, you will have that from this observation. From this observation, you then have that the half reaction that takes place at the anode is going to be copper. It's going to therefore break down to copper 2 plus 2 electrons. Copper is going to break down to copper 2 plus 2 electrons. Copper is going to break down to copper 2 plus 2 electrons. So this one here, remember, what does this mean? So now you're able to see that copper is therefore going to release 2 electrons. Copper is going to release 2 electrons. And the loss of electrons is called oxidation. The loss of electrons is called oxidation when this copper gives 2 electrons. But now this kind of half reaction takes place at the anode. Takes place at the anode. Let's look at the next question. How will the gradient of the graph be affected? How will the gradient of the graph be affected as the reaction is allowed to proceed until completion? Right, only increase, decrease, or remain the same? How will the gradient of the graph be affected as the reaction is allowed to proceed until completion? This graph. If you allow this reaction to go on until completion, the mass of copper deposited. What do you think, Nombuso? Let me give you a chance.
Remain the same.
Copper. Well done. It remains the same. Remain the same. Well done, Nombuso. Remain the same. Remain the same. So it's going to remain the same. Very well done there, Nombuso. Now we look at 9.5. Refer to the relative strengths of reducing agents to explain why zinc will not be deposited at the cathode. To explain why zinc will not be deposited at the cathode. Right, let us look at this here. Right, so now if you look at zinc, you need to compare the zinc and copper. So this is like looking at the zinc copper cell. You have copper, which is Cu2 plus 2 electrons gives you copper. And then you have the zinc. This is the zinc. What we're able to see is that this is the top of the table. And the arrow is going up like this towards the top of the table. And this is increasing oxidizing ability. And then now, if you go down, it's increasing reducing ability. So zinc is, because of this, you need to compare the strands. Right, so now we know that zinc is a stronger. Is a stronger reducing agent. Is a stronger reducing agent than copper. is a stronger reducing agent than copper. Therefore, is a stronger reducing agent than copper. Therefore, is a stronger reducing agent than copper. Therefore, copper 2 plus ions. Copper 2 plus ions will be reduced. Will be reduced to copper. So now the fact that if you look at this table, you actually have the positions of these. I want us to look at these very, very carefully. You're able to that if this is the top of the table, and then if you go up, it's increasing oxidizing ability. Increasing reducing ability when you go down. So you're able to see that zinc is at the bottom. So now there's increasing reducing ability. So which means that zinc is a stronger reducing agent because there's increasing reducing ability. So zinc is a stronger reducing agent than copper. Therefore, the copper 2 ions will be reduced to copper. Because it is a stronger reducing agent than copper, therefore the copper 2 plus is going to be reduced to copper. The copper 2 plus ions will now gain 2 electrons and therefore will be reduced to copper because the zinc is such that it's at the bottom. If you go down, it's increasing reducing ability. So that zinc is a stronger reducing agent than copper, and therefore the copper 2 ions will be reduced to copper. This is it. So that is the answer here you need to put down from the table of reduction potentials. You need to then say that according to the table of reduction potentials in 9.5, zinc is a stronger. Zinc is a stronger reducing agent. Zinc is a stronger reducing agent than copper. Therefore, copper 2 ions. Copper 2 ions will be reduced. Will be reduced to copper. Will be reduced to copper. So zinc is a stronger reducing agent than what? Than copper. Zinc is a stronger reducing agent than copper. Therefore, copper 2 ions will be reduced to copper. This is the answer. Why? This is the reason because you looked at the table at the strength of reducing agents to explain why zinc, Zn, will not be deposited at the cathode. And because of the zinc being a stronger reducing agent than copper, and therefore the copper 2 ions will be reduced to copper. 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 So we continue. We continue. We continue. We continue. Okay, let's look at the next question. Okay, that was 9.5. When the current flows for 30 minutes, 15 grams of pure copper was deposited at one of the electrodes. Calculate the number of moles of copper deposited for 3 marks. Let's look at this question. Let's look at this question. Grade 11s and grade 10s and matrix, you need to learn how to do chemistry calculations that involve mass. So now at this point, you need to use the formula to calculate the number of moles of copper deposited. To calculate the number of moles of copper deposited. I'm giving you 2 minutes, Nombuso. I'm giving you, what formula are you going to use, Nombuso? To calculate the number of moles of copper deposited. The current flows for 30 minutes. The current flows for 30 minutes, 15 grams of pure copper was deposited at one of the electrodes. Calculate the number of moles of copper deposited. Nombuso, what formula are we going to use? Which formula are we going to use here to calculate the number of moles? What formula are we going to use? Yes, please.
Okay. I think that the formula that we are going to use is that one of N is equal to small letter m over capital letter M.
Well done. So the number of moles of copper is mass over molar mass. So the mass is 15 grams divided. What is the molar mass of copper? What is the molar mass of copper? Okay, so this is the periodic table. And we're interested in finding the molar mass of copper. Right, what is the molar mass of copper? It is 63.5 grams per mole. 63.5 grams per mole. Which is 63.5 grams per mole. And therefore, this means the following. Let's use our calculator, which is exactly 15 divided by 63.5. And the answer is 0.24. 0.24 moles. Right, so this is actually exactly 0.24 moles. Right, so this is exactly 0.24 moles. Right, so here you're going to put 0.24 moles. 0.24 moles. Then you're going to look at the next question now, because now we know the molar mass, the molecular mass of copper, the big M. So the molecular mass of copper is from the periodic table, grade 11 and grade 12. Please take note of this. The molar mass is measured in grams per mole. Grams per mole. So let us look at the next question. When the current flows for 30 minutes, 15 grams of pure copper was deposited at one of the electrodes. Determine the number of moles of electrons. Number of moles of electrons that flows through the circuit while 15 grams of copper is deposited. Okay, we're going to do the corrections here, but I'm giving you 2 minutes. Anyone, Nombuso Pehalelo? I'm giving you 2 minutes. Anyone, be it Nombuso Pehalelo? I'm giving you 2 minutes. Determine the number of moles of electrons that flows through the circuit while 15 grams of copper is deposited. Right. Right, 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 right. Right, 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 right. Okay. What is the answer to this one? 2 marks. I'm testing you. You don't just get all the answers, you think also. I'm testing you so that I can see that you think also. I can see that you think. So we need the number of moles of electrons. What is the number of moles of electrons? Number of moles of electrons. Either numbers or Pechalelo. I know this is quite tricky, but I'm testing you. Pechalelo, we are going to spend a lot of time on your grade 11 stuff also, because I know that this paper is going to mostly be written by the matrix tomorrow. That is why I'm trying to make sure that Nombuso is better prepared for tomorrow. It's not that I'm just loving the chemistry. I want to make sure that Nombuso has a chance to understand the things for tomorrow. But Nombuso, what is the answer to this question? If you can't see, talk to me. Perelelo or Nombuso, anyone, please answer the question. 2 marks. I know it's tricky, but it's only 2 marks.
So,
Yes. You have never seen this before.
yes, but I can I try me?
Yes, please.
Okay. I think say the thing that we are going to do,
Yes.
we are going to apply the equation of n is equal to m over n, capital
Yes.
letter M.
Yes. So you think that we're
Then
going to use the equation that says that N is M over big M, like this, yeah? Which is number of moles is mass over molar mass, yeah?
then um they gave us the the mass of copper,
Yes,
which
they
is
gave us the mass of
15.
copper. The mass of copper is 15. So you know that the mass of copper is 15 grams, right? Just write 15.
Yes.
Yeah, good. Next.
Then over the molar mass of 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 copper.
Okay, the molar mass of copper. What is the molar mass of copper? We just read it out and we can just check it again. The molar mass of copper Cu is 63,5. So the molar mass of copper is 63,5, yeah? So it's 63,5, and then we're going to use our calculator to do this one. I'm testing you. I want to see what you're going to do. Okay, I'm testing you because I don't want you to slip. So then you're going to have 15 divided by what? 63.5. And then the answer is what? 0.236. 0.236 mole. Yeah? But we want to determine the number of moles of electrons. So what do we do? The number of moles of electrons. These are number of moles, but how do we get the number of moles of electrons? How do we get the number of moles of electrons? How? What do we do?
Okay, so I'm stuck here.
I know Pehelo is thinking about it. You think about it, Pehelelo.
Yeah, I'm trying, sir.
Okay, we're gonna come back with a lot of grade 11 stuff next weekend. A lot of grade 11 stuff next weekend. Okay. So it's just that today I'm just doing a few because these guys are writing chemistry tomorrow. But now you're gonna remember that we did this one. We did this one. Copper, we wrote down the half reaction that takes place at the anode. We said copper releases 2 electrons. So we have copper, which yields copper 2 plus 2 electrons. So you come here. We said copper releases copper 2 plus 2 electrons. We're coming a lot this coming weekend. Please, intense grade 11 revision, but intense grade 11 revision, please. It's going to be hectic. A lot.
Okay, so wait. Okay, wait.
Oh, okay. I
Stop
must
there.
wait. Huh? Oh, okay. Who am I talking to?
Helen.
Oh, okay. That's fine. I'm happy that you're trying. Thank you so much. And we're going to do a lot of chemistry revision this coming weekend. Please, like a lot, a lot. So, a lot. So you must prepare. You must be there. You must be there. You must be there. You must be there. A little bit tricky for some 2 marks. See, the marks are 2. We're at the end of the paper. The total is 150 marks. 150 marks. That's the total of this paper. It was written last year, not very long ago, like last year.
Okay, sir.
Right. Yes. Mm-hmm. What do you think?
So,
Yes.
I see that we found the moles of, is it zinc? Yeah,
Yes,
I
yes,
think
yeah.
it's,
I understand. That's fine. That's fine. Yeah.
so, so we're gonna use the mole ratio to find the,
Excellent. We're gonna use the mole ratio. Well done. I can't believe this. This is brilliant stuff. This is brilliant stuff. You're gonna use the mole ratio. Did you hear that also, Nombuso? We're gonna use the mole ratios. Now, in short,
Yes, sir.
because that is the correct thing. Now, what we normally say is that the number of moles of copper, the ratio of the number of moles of copper, the number of moles of copper is 2n, the number of moles of the electrons. At this point, we use this ratio. So, I mean, Pekala is on point. I can't believe this, but this is awesome, 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 awesome. So now we come here and then say the number of moles of the electrons would be 2. It's 2 times the electrons. So now if you want to find the number of moles of the electrons, you then say it is 2 times. You have already got the number of moles of the copper, which is 0,236. Okay, so it is 0,236. And then now when you multiply these two things, wow, I mean, this is exactly what needs to be done. I was just testing you. I was just testing you. I did not expect any answer, but I said, let me just test these two guys and see what they're going to say. Okay, so this is 2 times that, which is 0.472. 0.472. And this is the answer. So you're going to say 0.472. Then we say mole of electrons. 0.472 mole of electrons. We get our 2 marks, and this is the answer to the question. It was so awesome having this discussion with you guys. I'm going to make this recording available in the next
oh,
couple of
so I'm so
minutes.
sorry.
Yes.
Oh, so I said zinc instead of copper. I'm so
That's
sorry.
fine. That's fine. I understood. I understood that you're on the right track.
Yeah.
You were on the right track. I understood. I understood that you're on the right track, but this is the answer. So I was excited when you said you're gonna use ratios. You're gonna use ratios. And I was like, wow, that's exactly what you need to use. You noted that number, so? Okay. I must thank you guys for joining us. It was awesome. It's just after 10. I must let you guys sleep and chill and revise your last things before your chemistry exam tomorrow. But I'm going to make this recording available for you guys to watch. Thank you. Thank you again for joining us. I'm going to check you again, guys, on WhatsApp so that we can have more discussions. But next weekend, we're here. But even during the week, I'm going to see if you guys are busy and if we can do something. If you're not busy, we still can learn more mathematics and more science. But thank you guys for joining us. Until next week or during the week, I'm going to check with you. Take care and goodbye. Goodbye, guys.
Bye,
Goodbye.
sir.
Bye, guys. I'm going to send you the video soon. Thank you. Goodbye. Goodbye.